Hi, my name is Paul Abernathy, and welcome to today's presentation here at Master the NEC, where we're going to talk main bonding jumpers. And we're going to talk about supply-side bonding jumpers as well. We're going to talk about sizing them, and we're going to talk about the different nuances using certain tables in the National Electrical Code, most notably 250-102C1, which is new for you if you're in the 2014 NEC. Previously, when you did supply-side bonding jumper sizing, it would end up reverting you back to 250.66. And we'll talk about all that. But we're talking about the 2017 code, and we're going to look at these tables, and we're going to do some sizing. But we're also going to talk about the proper bonding techniques on the line side or supply side of service equipment. So we can understand whether or not you can use bonding lock nuts, whether or not you have to have bonding jumpers, and all those type of things. We'll look at various examples of some equipment through some graphics and kind of illustrate some of the things. And then while we do that, we'll also get into remote meter bonding, what you have to do there, remembering that it is still service conductors going from a remote meter or even a meter disconnect onto the service equipment. So all of those things have to be taken into consideration, and we're going to look at all of those things during this presentation. So let's get right into the PowerPoint presentation. And again, this is a 2017 NEC. We will reference earlier editions where necessary, but for this case, we're going to deal with the 2017 NEC. So main bonding jumpers and bonding at the service, that's what the scope of this training is today. We're going to look at some definitions of bonding and bonding jumpers. We're going to look at the functions of a main and supply side bonding jumper, kind of what they do. We're going to look at sizing those main and supply side bonding jumpers. We're going to look at the methods of bonding at service equipment, most notably on the supply side of that service equipment. We're going to look at the use of the grounded conductor, or the neutral in some cases, for bonding on the line side or supply side of the service equipment, all the way up to the transformer, but mostly for us as electricians up to the weatherhead. But I guess it could apply if it's an underground service lateral and it goes over and it's a pad-mounted transformer that is actually owned by the premise. Then you know all of that is still service conductors if we're dealing with a utility type transformer. And then, of course, we're going to look at the requirements for grounding and bonding of remote metering. Now, main bonding jumpers and bonding at the service. The main bonding jumper is one of the most critical elements in the safety grounding and bonding system. Okay, the main bonding jumper serves as a link between the grounded service conductor, the equipment grounding conductor, and the grounding electrode conductor. So we'll come back to me here. So it's a key component that ties everything together in your panel. So we're all familiar with looking at normal panel in your home or something like that, and you've got your bus there, and your grounded conductor comes in, and it might be black wrapped with white tape, and it comes in and it goes to the actually grounded conductor bus, terminal bus. And in there, you usually will see a main bonding jumper installed. At that point, you'll also see the bare copper that leaves out and goes to a grounding electrode somewhere on that property, on that premise, using a grounding electrode conductor. So it brings everything together right there on the same bus. Now, there are some allowances if you're going to use a wire-type main bonding jumper to connect to, let's say, another equipment grounding terminal bus, and you connect the two together where that equipment grounding conductor terminal bus is connected to the enclosure, and now you're just trying to make those connections back to the grounded conductor, which is required by the code. That jumper, if of the wire type, has to be sized, and that would be a main bonding jumper that we size in accordance with 250.20 AD. So we'll look at all that as we get into more of the presentation. All right, so in this presentation, it connects the grounded service conductor, the equipment grounding conductors, and the grounding electrode conductor together. Now let's talk about some purposes here, because we're talking about the main bonding jumper, and it has a distinct purpose. Now, the primary purpose of the main bonding jumper is to carry the ground fault current from the service enclosure, whatever might energize the enclosure on a ground fault condition, and from the equipment grounding conductor system that is returning to the source during a ground fault condition. Okay, so that's one thing. So if something gets energized onto the metal enclosure or something downstream via equipment grounding conductors, it comes back to that bus. That bus is connected to the grounded conductor so that it can get back to the source. Now, all electricity flows through a closed loop type system. So if you think about your house, if you have a switch and you switch it off, the light goes off. You turn it on, you make the connection with the switch, then the light goes on. You're completing that closed loop system. Well, that's the same principle here for the main bonding jumper. If that main bonding jumper isn't installed properly and there's a fault downstream that gets back to the service equipment, now it has to get over to the grounded conductor in order to get back to the source, which is at the transformer, in order to complete that closed loop system. If that main bonding jumper is missing, then what happens if you have a ground fault condition? There's a chance that you will not trip an overcurrent protected device. In fact, it's a good chance you will not, because you have effectively broken that effective low impedance ground fault current path by not following effective means of making it a complete system. Okay, so that's kind of one of the deals that we have. It's a critical deal too, to make sure that you're aware of that. All right, so next it ensures that equipment grounding bus is at the same potential as the earth, where the grounding electroconductor is connected directly to the grounded service conductor. All right, so let's discuss that again. So at that panel, it's typically the location, and we're not talking about the wire type that connects to a separate equipment grounding bus here. We're talking about the traditional one that you see. And we'll see some graphics in a minute, and I'll point that out. A regular panel or a regular piece of service equipment where the grounded conductor comes in, goes to the grounded neutral terminal bus. You're going to take all your equipment grounding conductors there. You're going to make sure you have that main bonding jumper in there. All your equipment grounds and your grounded conductors from your various circuits are all going to go to the same location, right? And that is where your grounding electrode conductor is going to go. That goes out to the electrodes within that premise. Now, that is critical because it ties everything together, but at that point, it also brings everything at the same potential as Earth, okay, in that connection. So that's a critical component there. And that becomes more critical later when we talk about supply side bonding jumpers and all those natures on the line side. But we're now talking about the main bonding jumper and its principal function. All right, next, the main bonding jumper completes the earth connection to the grounded neutral conductor, where the grounding electroconductor is connected to the equipment grounding bus as permitted in 250.24a. And I will show you an example of that in a later slide. All right, so we got to know some terms. Now, the first thing I'll tell you, when it comes to terms, they are critical. In Article 100, all the terms that you'll see in Article 100, except for the exception here of supply side bonding jumper, are all found in Article 100. Now, supply side bonding jumper is found in 250.2. I will tell you, for the 2020 National Electrical Code, there was a public input to move it to Article 100. Why? Because the style manual says that in 2.2.2.1 of the NEC style manual, that if the definition is used in more than one article, that it needs to be located in Article 100. That is under the purview of Code Making Panel 1. So the due diligence of Code Making Panel 5 would be to actually approve or agree with this public input in order to realign it with the style manual. Now, whether that takes place, we're yet to see, but that is the concept here, and it should move over into Article 100. It is used in many other places within the National Electrical Code. So the main bonding jumper in listed equipment. Okay, so let's say I buy listed equipment. And what I'll do is I'll come back to me because you see this on the screen. If I buy a panel board, and in that panel board it has a green screw, or it has a Z strap, or well, whatever you want to call it, an actual bonding strap that is manufactured as part of its listing. In other words, it was evaluated with that product standard. Then if you use that in the installation, then I don't have to do anything. I don't have to size it. I just simply accept it. Now, some people try to size it. It looks like a wire in some cases, and they might go, that's a wire. But it was factory designed, then it's perfectly acceptable. And various listing standards will allow for certain things within that listing, in that equipment, when it's evaluated to meet that application. Again, the long and short here is don't try to reevaluate. Now, if they take a piece of equipment and they remove the factory supplied device that makes that connection, or the factory supplied main bonding jumper, and they use of the wire type and they create it themselves, like adding an additional equipment grounding terminal bus rather than using the one common bus for the grounded conductor with the main bonding jumper in it, at that point, connecting the two is going to require a main bonding jumper, and that might be of the wire type, and of course, you're going to have to size it. Here we're just talking about factory supplied main bonding jumpers. Don't try to resize it or reinvent the wheel on that. Now, again, examples here would be a dead front switchboard in UL 891 would give you probably some main bonding jumpers that are supplied with equipment. Same here for motor control centers in 845. UL 67 supplies that, usually like a green screw or a strap. Power outlets, UL 231, and of course, again, furnished by the manufacturer. Don't reinvent the wheel here, accept what they do. Now, this is an example of the one I was talking to you earlier, whereas instead of the green screw being up here in this grounded terminal lug, they've actually added an additional, maybe they needed more terminations here. So down here, they actually put an equipment grounding terminal bus and they mounted it to the enclosure. And up here, typically, this is floating at this case because there's no main bonding jumper in it. But what they've done is they've installed the screw here, and they've now connected these two buses together to act as one, and they used a wire type main bonding jumper. Now, of course, if they do that, you're going to have to size this main bonding jumper. It is not factory installed. Okay. All right, so that's not to say you might not get a preset piece of equipment with a wire type with labels on it that comes from the factory and they've already done it all the sizing. That might be the case. But for the most part, if you see a separate wire in here connected to two separate buses, then what they've done is they actually sized a main bonding jumper here. Now, the reason I want to show you this graphic right here is simply to illustrate the connections here. Here you've got two PVC schedule 40 or 80. We don't signify at this point. Coming into this CT cabinet, here we see this CT cabinet bonded right here to the neutral conductor, and we'll talk about that later in the allowance for doing such a thing. And then, of course, you see them coming over, and of course, this enclosure is bonded to the grounded conductor at this notation here. Again, using the same principles that we did over here, right here. And of course, here are your two main breakers for your two pieces of service equipment, and they have what's called a main bonding jumper in those. And if that main bonding jumper is a factory supplied main bonding jumper, then you do absolutely nothing. If it happens to be a wire that's making this connection, then you're going to have to size it, and you're going to size it based on the size of these conductors that are supplying this piece of equipment. All right, and again, we'll get into all those details here shortly. All right, let's talk about the main principle of the code. It said the general rule was for grounded systems, all unspliced main bonding jumpers is required to be connected to equipment grounded conductors and the service disconnect enclosure to the grounded conductor within the electrical enclosure for each service disconnect. Okay, we saw that. And anyway, jumping back, that would be a principle here behind this. Whether it's factory supplied or it's a wire, it's making all these connections between the enclosure. And of course, in this location, you might have the grounding electroconductors going out. Of course, they could be here as well, coming from here. The code allows for that. But anyway, that's the general purpose here to make that connection where the service disconnection means is. However, you do have an allowance here where you have a piece of assembly that's listed as service equipment. So this operates under the 6 disconnect rule, and this piece of equipment could be a switch gear. And what you'll have is a common location where you'll have here a grounded equipment grounding bus that runs along the bottom of the equipment. It's just a common location that's common to all of these disconnects. And then what you'll have is the main bonding jumper that connects, just like you would in a regular panel system, the grounded terminal bus over to the equipment grounding bus. And that would be your main bonding jumper. And of course, we have to size that. Because it is of a wire type based on the size of the service entrance conductors that are supplying this equipment here. And then you have, again, here are the grounded service conductors coming in as well. Okay, so this is an example of some switch gear, and it states right here in the code, it says where more than one service disconnect means is located in an assembly listed for use as service equipment, which is what we have here. An unspliced main bonding jumper is permitted to bond the grounded conductors, these right here, to the assembly enclosure per section 250.24b exception number 1, which is this allowance to do that. So really the exception said that the general rule means that I would have to make it in all these locations where there's service disconnects. But this exception allows you to do it in a common location in a piece of a listed assembly as service equipment. And we're doing it, and this might be in the bottom of the switchgear, might be on the side of the switchgear. In this image, we're just showing it here to depict the fact that the two are connected together. And the one thing that I'll tell you, and I'll bring it back to me, is don't get overwhelmed by whether you're dealing with a simple residential panel or you're dealing with a large piece of switchgear. The principles still apply to both. You just have to look a little bit. One's going to be a lot bigger and more pronounced than the other. But don't let it get complicated. In this example here with this graphic, this was a large piece of switchgear with the 6 disconnects in it, complying with the 6 disconnect rule. And so in this piece of equipment, it would be infeasible to make these connections at each one of those individual disconnects. So because of this allowance in the exception, I'm still doing the general rule. I'm still taking the grounding conductor and connecting it to the equipment grounding terminal bus, which ultimately is connected to the enclosure. And we're meeting all those requirements. We're just able to do it at a separate location within that piece of equipment because it's a listed assembly rather than each one of those service disconnect applications. Okay, so that's what makes it kind of an exception, but really you're still meeting the intent that you were supposed to meet originally in the general rule. Now, this is an example of where you might have those two buses connected together using an actual factory supplied strap. And this is what you see here. This is the main bonding jumper that's connecting the neutral terminal bus over to the equipment grounding bus or bar. And this, again, this one will be factory. And you don't need to resize this. This has already been determined by the manufacturer in their testing when they got the listing of this equipment. Here's an example of a strap that was provided again by the manufacturer that's connecting both the grounding conductors and the looks here like the grounding electrode conductor and the metal enclosure all connected together. You'll have the literature that'll say where this strap goes and how you make this connection, and that is all again supplied by the manufacturer. So here's just some examples of the other type. Again, here on the right we do see another bus bar that was made that makes that connection, or a strap. Here we see a real common strap that we see in a lot of residential type of panel boards or panel enclosures. This one right here. Because this allows you to remove it if it's going to be used downstream as a remote distribution panel or whatnot, or different applications. So here you install it. And of course, a lot of times we see a simple green screw. And you notice that it has torquing values on here. That gives me the opportunity at this point to talk a little bit about torquing. Now, torquing is a requirement of the National Electrical Code. Now, it's surfaced as a new section in the 2017 code, 110.14d. However, torquing is not new. It was been in the code for many, many, many years, and that was found in 110.3b because the manufacturers put values on their lug torques for their piece of equipment that they sell to the consumer or the electrician or whoever uses it. And when you're going to make that termination, you need to make that termination inch-pounds in accordance with whatever the manufacturer tells you. If you don't do that, then you're really violating the listing via 110.3b. So while it's in the code in the 2017 under 110.14d, it is not a new requirement. It's just a new section within the code that's bringing attention to something that's always been there. Now, what is new in 110.14d is that it's requiring a calibrated torquing tool. So, and it doesn't say anything about ongoing calibration, which is probably a good move to make if you're have a project and people drop tools all the time. But when you buy it, you'll get it. It'll have a certificate that says when it was calibrated, and that certificate is what you're going to show to your electrical inspector. Now, whether they want to check all your torques within a structure, and that could take all day, probably not, but you at least show them that you have that certification that this torquing device has been calibrated. And at that point, many jurisdictions are going to determine what they do, whether it's an affidavit, whether they say, look, I'm going to trust you. You're the electrician. You torqued everything. You showed me the certificate. I'll accept this affidavit that says that you've torqued everything in this structure in accordance with 110.14d and that calibrated torque tool. Everything's good, and I'll accept it. But torquing is critical because when we're talking about wires, if you over torque it, you damage the conductor. If you under torque it, you're not making a good connection. Both of those situations can cause unnecessary arcing and heat rise. And that heat rise over time by R squared can cause an issue of the termination and cause system breakdown. So it's so critical to make those torquing terminations properly. So that's what 110.14d is going to attempt to do, brings in that calibration requirement. But remember, 110.3b has always been there. So if you're not in the 2017 code, you still got torquing requirements. And the actual electrical inspector can actually request to show proof that you did those torquings per the manufacturer's specifications. So just keep that in mind. Sorry to digress, but I do want you to know that there's torquing requirements for everything almost. For example, even fittings on MC cable, AC cable, things like that, FMC, the connectors, all of those, the screw sets have torquing requirements that have to be maintained. Now, I know we probably don't all do that, but there are torquing requirements that could be requested at any time by the local jurisdiction. All right, let's get back to the presentation, and I will do my best to get back on track here. So here are some of the representations of some of the main bonding jumpers that you might see within different relative service equipment that you might encounter. Here's an example of the screw actually being put into a piece of equipment here, and it's a threaded entry. You can't see it behind here, but here's an example of a hole here. It might be threaded here, and the screw screws right into it. Many times this is loose or not even screwed in, so you do have to make sure it's in. And again, it does have torquing requirements. In this case was once you get past the original torque, then you torque it to 35 inch-pounds and you're good to go. Here's another example of a strap that's utilized from the manufacturer. Again, no need to size this. I'm not sure how you would calculate it because it's not necessary. The manufacturer does a lot of testing on this to make sure that this can handle the potential ground fault current imposed on it during a condition for the rating of this equipment here. And so no need to reinvent the wheel here when it comes to that. Now, what are the functions of the main bonding jumper? Not to get repetitive on that, but I think it's critical that we also just reiterate that it connects the grounded service conductor and the equipment grounding bus or conductor and the service equipment. It ties everything together. It provides that low impedance ground fault current path for current to get back to the source. That's a key thing to allow any overcurrent protective device downstream to actually trip. Okay, many of these overcurrent devices, it takes 5 to 6 times or even more, depending on the trip curves, in order to cause it to clear on a ground fault condition. All right, so with that said, you want to make sure that you have that main bonding jumper in there because that does provide that low impedance effective ground fault current path. At least it gives it the best effort to do so, and it provides that closed loop that we talked about earlier. Also, it connects the grounded service conductor to the grounding electroconductor, where the grounding electroconductor is terminated on an equipment grounding bus or bar where a wire-type bonding jumper is used. Remember that one because I'll show you that in a minute where, again, as you saw it earlier, it's that wire that connects the two buses. If that's your orientation that you choose on your installation, rather than put everything on the same bus, then that wire type, once you size it, you can bring the grounding electroconductor to that equipment grounding terminal bus, provided that you use a wire type bonding jumper or bus bar. Okay. So, and we'll look at it in this graphic. So let's kind of look at an overview here. So here's your transformer. Here's the grounded conductor. Here it comes to this one common bus where we're going to bring everything here. All of our grounded conductors. We're going to bring our equipment grounding conductors all here, just like you'd see in a normal panel. 20 circuits here, 20 circuit breakers. Everything's good. This panel downstream is a remote distribution panel here on the right. It is sometimes referred to as a sub panel, but I've never seen it installed in a sub, nor have I been in a sub where I've seen a panel like this. Really, sub is a derivative of the fact that it's subset of the service equipment, or it's a downstream electrical panel. So really, we call it remote distribution panel or remote panel, however you want to call it. Here's what it is. And you'll notice on this end, you have two different bus bars. Here's the grounded conductor bus bar, which is isolated. I show this by the yellow with the red around it. And then over here, the green means this one is actually connected to the enclosure. It has an equipment grounded conductor downstream. As we all know, you're required to have 4 conductors feeding remote distribution panels in order to have a separate grounded conductor, and in our case here, a neutral, and a separate equipment grounded conductor bus. Okay. And let's see here. All right. So actually, I'm getting all these pop-ups. Okay, sorry about that. All right, so here, this equipment grounded conductor, if there's a fault downstream, it comes back here to this bus, which it incidentally goes to the grounded conductor. If there's a fault in this piece of equipment over here, it comes from the equipment through the main bonding jumper over to the actual grounded terminal bus. and allows for the overcurrent protective devices to trip. Now, in this case, this might be a factory installed main bonding jumper, which is no sizing required. If it was a wire, again, you're going to have to size it. We'll talk about that in a second. So here's the one. Remember I talked to you earlier about the option to have the two different buses. So this one is the one they connect to the enclosure using the actual screws that in a little kit that's provided with this enclosure from the manufacturer. They make that connection and then you have to connect it over to the grounded terminal bus. And they do that through a main bonding jumper. Now, if this is the choice and it's a wire type main bonding jumper, then they're going to have to size this, and we'll talk about that in a second. Ultimately, it's going to lead us to 250.102C1 for sizing this, but that's the configuration they'll do. Now, everything else down here didn't change. It's simply showing you two options for two types of configurations here. Now, this is the one where I show you that when you do this setup, the code does permit you to bring the grounding electrode conductor to this terminal bus when this is of the wire type, okay? And that's the one we're sticking with. Because I happen to work for a wire and cable manufacturer, and we're going to go with that. So here you go. So here's the two buses tied together. This is the option here. Now, if this part down here wasn't there and everything's being done by one bus, then this obviously this grounding electroconductor would make a connection up here to this bus because it's required by the code to directly connect to the grounded conductor or the bus that connects to the grounded service conductor. Okay? But this is an allowance in the code to do it this way if you use this of the wire type. All right, now sizing that main bonding jumper, let's get into that. The main bonding jumper must carry the full ground fault current of the system back to the grounded service conductor, which may be the neutral, okay? But you always have a grounded conductor, but you might have a neutral, depending on the system you're dealing with. Now, if you're residential, most all the time, you're going to have a grounded AC system, okay? Now, size must relate to the rating of the service conductors which supply the service. Remember that. Okay, we're sizing this main bonding jumper based on the service conductors that are supplying the service. Now, the minimum size of the main bonding jumper is determined from the requirements of 250.28D. Now, 250.28D ultimately is going to send us to 250.102C1. But since this is the more complicated of the application here where I separate these two buses out to kind of keep you thinking all the time, here's our transformer. It comes down, no meter shown for simplicity of the graphic here. And it comes in, so we have our grounded conductor here. In this case, it is going to be a neutral because of the configuration here and because it is connected to earth. It is truly a grounded conductor. And so it comes over here, and now I've got the bus over here, which I didn't have enough room, let's say, over here for all the grounded conductors and equipment grounded conductors. So I added a separate bus. This bus is bonded to this enclosure by a factory kit. And now I need to connect these two together with a main bonding jumper of the wire type, so I have to size it. All right. The size of the main bonding jumper conductor is based on the size of the largest ungrounded service entrance conductors. Okay, so in this case up here, that's what we're going to do. Now, what size would that be? Well, let's see. If it was a 500 kc mill coming in for whatever reason, then I have to go to this table. Okay, so let's do that. So here we're going to go to the NEC, and we'll see here on the right that if it is and it's copper, we always assume copper unless stated otherwise. It is a over 300 through 600, then it's going to be a 1/0 right here. So if it's over 350 through 600, it would be a 1/0. So let's go back to the presentation. So this main bonding jumper right here would be a 1/0, and that would be sized based on the largest service entrance conductor supplying this piece of equipment. All right. Now, key note is if the values of these conductors are over 1100 kc mil copper or 1750 aluminum, then you got what's called a note 1 to that table, and we'll see that in a minute, but that's where a 12.5% of the largest service entrance conductor or the area, if they're in parallel, kicks in. Okay, so that's what we're going to do for there. And don't worry, we're going to cover all that to make it really easy to understand. All right, let's do an example of a sample. I'm going to get you this. We're going to work through this together. The first one, let's say we have a 250 kc mil aluminum service entrance conductor. We just shifted gears here. We went over to aluminum. All right, and we got to go to table 250.102C1 in order to be able to size what we need for this 250. All right, so let's go to the code. So we know it's 250 aluminum, so let's go to the NEC. So the NEC, and at this point, let's get rid of that, and let's kind of make this a little bigger, and we'll drag it over here a little bit and go up. Okay, so what do we got here? We know it's 250 aluminum, so we're in this column. Now, granted, it says the size of the largest ungrounded conductor or equivalent area for parallel conductors. Okay. All right, so in this case down here, what do we got? We said it was 250 aluminum. Well, some people make the mistake and go here. All right, and that says over 250. Don't make that mistake. You go right here. So it's the 4/0 or 250 size of the conductors. You're going to need either a 4 copper or a 2 aluminum. So that's your choices here. It would either be a 4 copper or it would be a 2 aluminum. All right, now we're not going to get into the other part of the notes just yet, but what I want to do is come back to the presentation, and we'll see what we sized it right. And there you go. So the size here would be a 4 copper or a 2 aluminum, whatever the choice may be. Yes, and you can also use copper-clad aluminum. Don't see a lot of it out there, and my primary conductor of choice would be copper, but there's absolutely nothing wrong with aluminum. And yes, you can get bonding jumpers in aluminum. Okay, the wire, obviously we sell plenty of aluminum wire. You can use the aluminum wire as a bonding jumper. Okay. And here's a table we just saw earlier. Again, I could have just done that rather than go to it, but here you go. Here's the difference. We're looking at 4/0 or 250. That our issue was 250 aluminum, and here's how you size it right now. Now you notice is these note 1 and 2 here. So anytime I'm dealing with over 1100 copper or over 1750 aluminum, you'll have a note 1 and a note 2 to deal with. All right, so we're going to look at that here in just a second to cover those. Now, let's size another one while we're at it. All right, so now we've changed it up a little bit. We're bringing in 3 sets. So there's 3 parallel sets of 500 kc mil in the same application. And we'll see a graphic of that in a second so you can kind of get a visual if you've never seen one before. Hopefully you have, but if you never have, we'll have a video picture for that. So you got 3 500 kc mil copper conductors are installed in parallel as service entrance conductors. Okay, so now we're sizing that main bonding jumper. So you add the circular mill area together, and if larger than 1100 kc mil copper or 1750 aluminum, you got to use a 12.5% rule. All right, well, in our case, we did. We have 3 sets, so you take the largest phase conductor, ungrounded service conductor in each raceway. And so you don't add them all up. You know, in this case, you don't add the 3, the 3, and the 3. You're just taking the 1 from each raceway. You add them together. So in this case, it's 500, 500, and 500 because we have 3 parallel sets of 500 kc mil. And they're in separate raceways. And so 3 times 500 is 1500 kc mil. Now, 1500 kc mil times what we just talked about, 12.5%, or using the decimal version is 0.125, or if you have a calculator, you can do 1500 times 12.5%, however you want to do it out. And it equals 187,500 circular mils. Next thing I got to do is I got to go to Chapter 9, Table 8. So we're going to do that. So let's go to Chapter 9, Table 8, and let me go to the NEC. And so I'm going to go over here. I'm going to bring this back out so that I can do that. And we're going to go to Chapter 9, Table 8. And there. And we're going to go through the tables and find Chapter 9, Table 8. Oh, I went one too far. Okay. So let's reduce this down so we can kind of see the whole thing. All right. So we said that we needed 167,000. In fact, let me look here. No, we need 187,500. Okay. So when we need 187,500, we have to find a conductor in those circular mills that are going to be adequate for that. So in this case, what if we picked a 3/0? Well, that's only 167,000 in here. That's certainly not enough. It's about 20,000 circular mills short. So we have to go to the next one. In this case, it would be a 4/0, which is 211,600. That's what we're going to need to use in this application. All right. So let's see here. Let's go back to the presentation. Let's see what our result was here. We know that we need to have a 4/0. And there you go. The next conductor that would exceed 187,500 circular mils is a 4/0 conductor. All right, so that's how we do that when we're sizing the main bonding jumper and we have a parallel application. All right. Now, let's talk about those notes for a second. We just said it, and I wanted to remind you again, if it's over 1100 copper or 1750 aluminum, then the grounded conductor or the bonding jumper shall have an area not less than 12.5%. So that's where we get the 12.5%. Okay. I will remind you that it also tells you that the grounded conductor or the bonding jumper shall not be required to be larger than the largest ungrounded conductor or set of ungrounded conductors. Okay, so you could be doing this based on the number of parallel sets, and you could do the 12.5%, and it could result in a bonding jumper or grounded conductor that may be larger than the largest ungrounded conductor or set of ungrounded conductors. And of course, they're saying you don't have to do that. Okay, very rare, I think, to come into that. For most people who are going to run into it, you're going to have examples like I did, where you have parallel sets of 500s, and when you do the 12.5%, it's not going to be larger than what you had as far as the conductors. All right, note 2 is a unique one here, and we're only going to deal with one aspect of it, the note 2, because I captured both note 2 and 3. We're really just looking at note 2. And the important part of this says, look, if the ungrounded supply conductors are larger than 1100 kcmil copper or 1750 aluminum, and if now that's an important and if the ungrounded supply conductors and the bonding jumpers are of a different material, copper, aluminum, or copper clad aluminum, they're a different material than what you're using as the bonding jumper, then the minimum size of the grounded conductor or the bonding jumper shall be based on the assumed use of ungrounded supply conductors of the same material as the grounded conductor or bonding jumper, and will have an ampacity equivalent to that of the installed ungrounded supply conductors. Okay, so basically it's saying is if let's make sure we cover it. If I'm using a bonding jumper and the material of that bonding jumper is different than what I used for the ungrounded supply conductors, then I'm going to actually size that main bonding jumper as if it was the same material as the ungrounded supply conductors. Okay. All right. Just to reiterate, the minimum size of the grounded conductor or the bonding jumper. So the minimum size, if you have differing materials, the size of those jumpers shall be based on the assumed use of an ungrounded supply conductor of the same material as the grounded conductor or the bonding jumper. Okay. So if I have aluminum conductors and I have a copper main bonding jumper, then I'm going to size this main bonding jumper based on ampacity of whatever the size would be that's equivalent to whatever the aluminum conductors were in of the copper equivalent. Okay, that's a lot of words, but again, just bringing you to note 2 that states that. And again, one last time for all of you. And also, this only applies when you're dealing with larger than 1100 kcmil. Okay, again, if the ungrounded supply conductors are larger than 1100 and 1750, and if the ungrounded supply conductors and the bonding jumper are two different materials, in other words, the aluminum conductor's coming in and the bonding jumper is copper, the minimum size of the grounded conductor or the bonding jumper, now we're talking about this, how you size it, shall be based on the assumed use of ungrounded conductors of the same material as the bonding jumper, right? So again, aluminum conductors coming in, the bonding jumper is copper. You're going to size that bonding jumper, the copper is copper bonding jumper. You're going to determine what size those conductors are that are coming in as if they were copper, just like what the material is for the bonding jumper, as far as using the ampacity to size it. Right, where it might be, for example, a 250 aluminum, the equivalent to it would be, if you did that equation, I'm just using this as an example, the equation to that would probably be a 300, a 3-aught copper. That would be equivalent to the 250 aluminum. Now, again, this only applies to those over 1100 and 1750, but I'm just using that as an example how you would do that using the ampacity. Okay, I did that 3 times, so hopefully I got that right, and I won't get a bunch of hate mail saying I got that wrong, but that's how you do it. I can tell you in my career, I've done that very few times. I've never had that much application where usually I'm using the same material or it's a factory installed bonding jumper, which you don't have to do. If it's that case, you don't need to worry about it. So we wanted to give you that example here of the 3 raceways in parallel. And here it is. Step 1, 3 sets of 500s. This is kind of what it would look like. And if you go to 250 to 102C1, it's going to say that here, this main bonding jumper, if this is not a factory installed, then it's got to be sized based on here. So it would be 500, 500, 500, 1500. And just like we did, it results in 12.5% results in, I think it was 187.50. And we had to go to Chapter 9, Table 8 to determine a 2160 circular mills, which equates to a 4/0. And that's how we did it. Again, just to show you, this could be a lot bigger than a normal panel in your house. But what I wanted to show you, if you break it down in simplicity form, here you've got the grounded conductors right here, connected to the grounding electrode conductor to the grounding electrode system, and the main bonding jumper connecting this enclosure and all of this together. And these 2 halves are actually bolted together. Okay. All right. So that is kind of in a nutshell. It really didn't matter what size it was. All of those principles, they might come in different forms and flavors, but you're essentially doing all the same things. So don't get overwhelmed by the size of a system. All right, so now let's look at the definition of a supply-side bonding jumper. Now, this is found in Dot 2 of Article 250. Again, for the 2020 NEC, it's going to be moved over, I would assume. I can't see why, and I sit on that code panel. And actually, we've had a meeting about this, and we've given our opinion on it. It belongs over in Article 100 because it is used in more locations within the National Electrical Code. And if you want to find that, get your PDF version and type in supply side bonding jumper and do a search, and you'll see that it comes up in a lot of different articles within the NEC. And that, of course, will be our substantiation for that within the first revision of the 2020 NEC. Now, what are the functions of the supply side bonding jumper? First, let's to make these easy, I want to get back to me and I want to talk about something. Remember, the supply side bonding jumper is everything that's on the line side or the supply side moving towards the transformer on the opposite direction of your main disconnection means inside of the service equipment. Okay, it is on the line side of it. The important thing to remember is there's no known overcurrent protective device on the line side. With that said, you're still required to bond all of these enclosures, raceways, meter socket, meter enclosures, all of it together. And we'll see that in requirements of 250.92a. But you tie all those things together because there's service conductors within it. And while there's no known overcurrent protection device on the supply side, there is still a chance there is one on the primary side of the transformer. Now, the utility utilizes that. We can't guarantee it's there, but we're going to give it a fighting chance to provide that low impedance fault current path back so that just like we talked about earlier with the main bonding jumper, we're going to give them a chance to possibly clear a fuse or something and make it a safe condition. Well, even if we don't do that, we're still required by the code to tie everything together to bring it to the same potential, and that creates a safer environment on the supply side. At least it gives a fighting chance. All right, it does connect everything to earth because back at that transformer, that grounded conductor is connected to earth by a chain of ground rods as well. So, yes, it's not going to trip any overcurrent device that we deal with, but there is a fighting chance, and the code requires it all to be bonded together as well. So I wanted to give you that overall understanding before we dig into some of the language. That way you kind of understand it better as we delve into it. Did I actually say devil into it? There you go. So a supply side bonding jumper provides electrical continuity between the supply source, such as a utility transformer enclosure, and the various enclosures, could say that, and raceways of the service equipment. Okay, so all of that gets tied together, provides that electrical continuity between them all. And theoretically here, we're bonding it all together. It connects bonding bushings where used, because you might have bonding lock nuts. If we'll show you where they're adequate. To service grounded neutral conductors in the service equipment enclosures. Again, that's the jumpers that we're going to talk about, which ties all of them. Like you might have an open bottom switch gear, and you got raceways coming in through a service lateral, and you still have to bond those raceways because they do have service conductors in it. So we're going to have supply side bonding jumpers over to those as well. So we'll cover that. It carries ground fault current from ground faults that occur on the supply side of the main overcurrent protection. Again, we talked about that. And if I showed an example here, it makes the connection here. All of this stuff here is really on the supply side of the service equipment. Here are your service disconnects, okay? So the main bonding jumper here. So if these were metal raceways and we had to bond them, we're going to do all that bonding here, and that is considered supply side bonding jumpers. But we're going to see all that here in a minute. Okay, and it provides a low impedance path for ground fault current to return to the source. Again, we're going to try to give any fuse that might be on the primary side of that utilities transformer the chance to possibly function. Okay, we can't guarantee it. Again, as an electrician, I deal at the service point into the premise. Okay, I'm dealing with premise wiring. I'm not dealing with utility aspects. So, we're going to give it a fighting chance, but we need to tie all those things together at the service equipments, meter enclosures, raceways, all of those locations that contain service conductors within them. We're going to tie them all together, and we're going to cover that. All right, so size, the supply side bonding jumper can be non-flexible metal raceway like a rigid IMC, rigid metal conduit, EMT, or the wire type. So I could have, obviously we have supply side bonding jumpers of wires. We do that all the time. And a lot of our examples here are going to be the supply side bonding jumpers of the wire type, connecting the enclosures to these different raceways. For example, we show a open bottom switchgear in that example. Now, service grounded conductor can sometimes also serve as the supply side bonding jumper. Yes, and we're going to see that application done in 250.142 here shortly, where it bonds all of the enclosures and everything together to the grounded conductor, which is perfectly acceptable on the line side or supply side of the service disconnection means. Now let's talk about sizing. On the line side of a service and main bonding jumper, okay, so we're on the line side of the service and main bonding jumper. We've already sized the main bonding jumper. We get that. Now, supply size per table 250.102C1. So that gives us our rules, and it says based on the size of the ungrounded service entrance conductors, use the rules in 250.102C. Now, if it's a parallel conductors that are run in a single raceway, just one raceway, then we're simply probably going to go to the table, and it's very easy to select it at that point under 250.102C1. But what happens if we have multiple raceways, 2 or more, and we're paralleling it out? And that was our example where we showed 3 coming into that piece of equipment. Then we're going to use 250.102C2 for that application. So let's look at the application where I've got multiple raceways coming in. In this case, it's an open bottom switchgear. It comes through the bottom, and it's sitting on a slab, and these come up through the slab. Probably didn't show that real well, but anyway, they're open bottom. So at the end, I have a choice here. I can run a single, what we call a supply side bonding jumper single, and loop it through all of these. Now, just like we did for the main bonding jumper here, since it's subjective to all of these raceways and we're running a single conductor, then at this point, we're going to have to size it based on the actual circular mil of all of the largest service conductor in these raceways. So in this case, I've got, let's say, 1 set, 2 set, 3. I'm running 4 sets here of 500 kc mil for our example. All right, so I go 500, take the largest within this raceway, Incidentally, since they're parallel, they're all going to be the same size of the largest ungrounded supply conductors anyway. So 500 set, because of the parallel rules in 310, we're going to go 500 to 500 to 500, 500, or easy for you, you can take all of the 500s in phase A, because usually they probably separate it out. In this case, ABC, 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 ABC. Anyway, long story short, 500, 500, 500, 500, that is 2,000 kc mils. We have to take 2,000 kc mils and do that times 12.5% because it is over 1,100. Okay? And we are using copper unless stated otherwise. If that's the case, this would result in a rather large supply side bonding jumper. Now, chances are, if you've ever done this before, you're going to see that these lugs handle wires, whether they're lay-in or feed-through, up to a certain size, and then they can't handle anymore. And you certainly don't want to use the wrong lug for the application. All right. So we have to make sure that we can do this. So one of the first things that you run into as an electrician is you might run into the fact that your lugs simply aren't large enough. And if that's the case, then you have to look at a different method. But for all of our intents and purposes, we need to look and see what size we would need for this single supply side bonding jumper. So we determine it is 2,000 kc mil, and we'll do that times 1.25. And that tells me that I need a 250 circular mil supply side bonding jumper. Well, that's pretty simple. I'm going to go and put a 250 kc mil through here. Now, again, if these lugs can't handle it, or they go up to a certain size, depending on the type of bonding bushing you have, then you might have to go to another option. And here's your other option. So in this option here, I am simply running a single in parallel to each one of these raceways. And I only have to use the conductors that are within this raceway. So I take the largest, in this case, ungrounded supply side conductor here, and I use that in order to size my supply side bonding jumper. So this was a 500 kc mil. Then this one's pretty easy. Then we're simply going to go to the table to do that. And simply going to the table, 250 102 C1 would determine the size we need. So we're going to do that. So let's go on. We've already done it, but let's go it again. So we're going to go back to the code. And of course, now I have to go all the way back to 250 102 C. And a lot of people out there will say, well, Paul, why don't you just use the search feature? And my answer to that is, I don't want to. I'm going to do it my way. I've been known to do it, always do it my way, and I'm going to do it my way. All right, so here's the table, and we determined it was 500, so over 3/0 through 350, it's not going to work. So here we got over 350 through 600. It needs a 1/0. Ours are copper for this example. All right. So now let's go back to the PowerPoint. All right, so that's what this jumper would be. And you know what? It's readily available to find a 1/0 rated lug that can handle 1/0, a lot more than you might find one that handles 250 kc mil. If you can find one and you want to run a single one through it, that's fine. But a lot of times this is the application that people use. Okay. Now, let's talk about parallel supply side bonding jumper, because that is talked about in 250.102C2 in the actual language. All right, it's talking about that. So when you have parallel service entrance conductors installed in 2 or more raceways or cables, along with the supply side bonding jumpers required to, or cables, along with supply side bonding jumpers, require the supply side bonding jumpers to be run in parallel as well. All right, so this would be an example of that. Okay, but if it's in a cable assembly and you're doing this and you're using a cable assembly that is allowed to be run with service entrance conductors, then you might run into something like this. Whereas here you have this, as long as it's not over 6 feet, and this is all covered within the National Electrical Code in 250.102. But if you're also looking for use for equipment bonding jumpers, then you'll see that you also are going to limit it to 6 feet, and you would have to maintain. So here's the fitting, and here's the fitting. The conductors are running here, but you got to maintain the integrity of this raceway to this enclosure. So you have to run in parallel the supply side bonding jumper, or if it's on the load side of the service disconnection means, then this would be what's called an equipment bonding jumper. Just wanted to point out it's done the same way, whether or not it's on the supply side or on the actual load side. Now, the only caveat to that, and what I want to do is I want to bring up the code. So I just wanted to show you what I call my FMC octopus here. If these were service conductors and you're doing this, and this was an acceptable flexible metal conduit type of allowance, then I would have to have this bonding jumper over it. Now, I could have one inside. This is an example shown outside. All right, so now let me go to the code, because I want to show you the actual code verbiage here, and I'll scroll down here. Let me find it here. 102C. Okay, right here. Now, this was the D, which we didn't show, but if you are installing equipment bonding jumpers on the load side, you would size those bonding jumpers based on 250.122. We're not talking about those. We're talking about the use of the service conductors. In 250.122 for equipment bonding jumpers on the load side, That's all based on the overcurrent protective device, okay? Because that's what 250.122 is based on. But what we wanted to look at is down here in 252E. This E is what we're dealing with here. It's using that glass example we had, okay? When they're run outside of the raceway or enclosure, now I want you to understand that E deals with both. It doesn't matter whether it's the supply side or the load side. This is dealing whether you're running it inside the raceway or you're running it outside the raceway. If you're running it outside the raceway, again, we're talking about bonding jumpers or conductors and equipment bonding jumpers shall be permitted to be installed inside or outside of the raceway. And if it is outside, like the example, the picture we just showed, it says if installed on the outside, the length of the bonding jumper or conductor or equipment bonding jumper shall not exceed 6 feet and be routed with the raceway or enclosures. Okay. Now it also gets you an exception. It talks about supply side bonding jumpers longer than 6 feet shall be permitted at outside pole locations and whatnot. So that's an exception to the general rule. So what I just want to do is to kind of illustrate my little octopus here, because it's kind of using this. I could switch the concept here and say that this had service conductors in it, and you're running this supply side bonding jumper in parallel based on 250.102E2. Okay, and you're going to size it based on the service conductors that were in that raceway. Or this could be done on the load side, same kind of configuration, and these would be what's called equipment bonding jumpers. And in that point, it's bonding over. And in doing this, you're going to size it based on 250.122, based on the size of the overcurrent protected device supplying the conductors that are within this cable assembly, all right, or conduit. All right, so that's just kind of, I drew this image because I wanted to show you both ways here that you're dealing with it. All right, this is an example of a fitting that you might use. This is one end where the jumper might go in here, and then you have a fitting that might be just a straight fitting on the other side that'll also have a lug like this, and you actually make the connection, and that would be what you would use to jump over the flexible material that goes in this end. And this is the end that would screw onto the actual enclosure. All right, let's talk about bonding service equipment enclosures now. There are special rules that provide for bonding enclosure on the line side or supply side of the service disconnection means. We're talking about on the line, not on the load side of the service disconnection means. Okay, all the stuff we've been talking about for supply side bonding jumpers take place on the line side. Now, all metallic enclosures that contain service conductors must be bonded together. We've established that in 250.92A, which we're going to look at the code here in a second. Now, this equipment does not have overcurrent protection on the line side. We've talked about it. Unlike what you have on the load side for feeders and branch circuits, where you can trip an overcurrent protected device using a main bonding jumper, here we're on the supply side, and they're not main bonding jumpers, but they are tying all metal parts together, and they are taking a chance that when you do so, and you size these conductors properly, that you might, or you make the connections properly, that you might clear a fuse on the primary side of the utility. Can't guarantee it, but you might. We don't govern that in the NEC. So here's what the code says. 250.92A, bonding of equipment for services. The normally non-current carrying metal parts of equipment indicated in 250.92A1 and A2 shall be bonded together. That means all raceways, cable trays, cable bus framework, auxiliary gutters, or service cable armor, or sheath that encloses, contain, or support service conductors, except as permitted in 250.80. And that's talking about those metal elbows that might be buried at least 18 inches in the ground. Okay, then there's really no way to bond that elbow. Okay. Number 2 says all enclosures containing service conductors, including meter fittings, I guess it also be meter enclosures, boxes, or the like, that is interposed. That means it's been put in place in the system between the service equipment and the utility. Okay, whatever's in there, and generally you're only going to deal with the portion that's at the service point towards the premise wiring. But if anything's interposed in that system, and it is metal, like maybe a meter disconnect, or like you said, a meter enclosure, or whatever, a CT cabinet, all of that type of stuff that's going to be interposed in the service raceway or armor at some point, all of that has to be bonded together. Okay. Now, when you do that, and you meet those requirements, it ensures that none of the electrical enclosures can become electrically isolated or an island to itself, which become a shock hazard. When you come in contact with it, you could make the connection to where the intended path is back to the source. We don't want any metal to be isolated. We want it all bonded together. We want to give that fuse, if one is there, a fighting chance. Now, provides a low impedance path for fault current, so the fuse or circuit breaker on the supply side of the electric utility, primary side, will open or operate. We hope that happens. Again, this is a regurgitation of what I just read for you out of the code. We're bonding all of these things together, all these non-current carrying metal parts together. So let's look at an example here. So here's our service, overhead service. This metal raceway here, which is in this case, we'll say it's rigid metal conduit. It's threaded into a hub, one of the items that it's listed to be in 250.92b. And then it connects to this enclosure, which comes and is connected through this enclosure to the grounded conductor, which you'll see this is perfectly acceptable in 250.142. We haven't gotten there yet, but you'll see that's a common application. And now all this enclosure, everything's tied together. Now you get to this raceway. In this case, let's say it's just the nipple. Now you're required to bond this raceway. Whether you do it on this side or you do it on this side is irrelevant. I have to bond it either side. So in this case, I'm bonding it in the service equipment panel. Now here's the supply side bonding jumper, and it connects over to the grounded conductor here. And this is sized based on the service entrance conductors that are feeding this service equipment. That's what it's based on. And we've already done that. We know how to size it. Now, if this is a main bonding jumper, if it's a factory installed, like a strap or whatnot, or it was a green screw in here, again, we don't do anything. If it is of the wire type, we're going to size it as well based on the size of these service entrance conductors that are supplying it. Okay? All of that ties everything together. Now, we're also going to get into what happens if these knockouts were impaired or oversized, concentric or eccentric, or the reducing washers were used, or there's some kind of damage to it. We're going to cover that here in a second. In this one, we're going to say that's probably a concentric knockout, so he used a bonding jumper here. Because if you encounter reducing washers, oversized, concentric, eccentric knockouts, or any impaired connection, then you're required to use a bonding jumper. So that means you're going to have a bonding bushing with a bonding jumper on it. If these were perfectly knocked out openings, means there's no rings left in it, or you punched them yourself, like in larger equipment where you have a hole punch, a Greenlee, for example, they make one, a hole punch. At that point, and you use the raceway on it, then you could use what's called a bonding lock nut. You can never use a standard lock nut for any of this special service type of bonding. You can use it for mechanical purposes to kind of hold it all together, but you can't use it to make that real important assured type of bonding connection. Okay, so in this case, we're going to assume that it has rings that had to be knocked out, and there's still a couple rings left in there. So here they use the bonding bushing, and it's mechanically held here by the lock nuts, standard lock nuts for mechanical purposes, and that's why he had to put a bonding jumper here. Now, it could have been done over here, but it was done over here. It doesn't matter which side. The only problem over here, and we'll show that in this graphic, is that many jurisdictions don't like this because they say that when the inspector comes, it's not accessible. The other, and it's so vital that this piece of raceway doesn't become an island, that it has to have this supply side bonding jumper. Now, here's the thing. I kind of lean towards it being over here in the service equipment. Why? Even though the code permits it over here, once this is all done and I sign off on this and now the utility comes to energize it, they might not like it and they might rip it out. If they rip it out, then I'm not, as an installer, I might not be coming back to this job. So I might not know that there's one in it. And so that means this nipple becomes isolated and it has to rely on these eccentric and concentrics or impaired connections, and we don't want to rely on that when it needs to make sure that it makes that connection. All right. Remember, there's no overcurrent protective device ahead of it that we're aware of, so we're going on a leap of faith that the utility has one on the primary side. So we want to make these connections done, and we want to make sure they're done properly. Okay. So that's here. So I like it over here, but the code does permit it over here. All right, now let's talk about that 250.142, which is so common in meter enclosures, and it really saves you a lot of money in your installation. Now, we love for you to use wire, but there's some examples where you don't need to have the supply side bonding jumpers. that you could actually use the grounded conductor for that connection. Now, you still use the supply side bonding jumper in the example that I'm going to show you here. So here we've got the raceway coming in. It's connected to this enclosure through a hub. This hub has got 4 screws on it. It bolts through threaded entry that is listed in 250.8. It's all acceptable. It connects to this enclosure. This enclosure is connected to the grounded conductor through this screw here, and I use green here to show that it's made that connection. All right, and that encloses all that. Now, this is all good. Now you get down to this raceway. This raceway, let's assume now that these have concentric or eccentric knockouts. Either they're center ringed or they eccentric out from the center. And I've knocked a few of them out, but I haven't knocked them all out. Well, because that is considered an impaired entry, we're going to have to use a bonding bushing with a bonding jumper. And here's my bonding jumper. I size this supply side bonding jumper based on the size of the conductors serving here. Okay? Now, what about this enclosure? Now, this enclosure right here, these are the conductors that are supplying it. So the connection here, if this was a factory installed jumper, then I wouldn't have to do anything. It's supplied by the factory. But chances are, in this here is a trough or wireway, chances are it's probably the wire type, so you're going to have to size it. And you're going to size it based on the size of the you're going to size it based on the size of these service entrance conductors that are coming in that could potentially energize this wireway. Now, what about this one over here? Well, we had the same situation. We're using concentric or eccentric knockouts. It's probably the standard. And so I have to bond this raceway here. Now, because of those knockouts, I have to use a bonding bushing with a bonding jumper. And it is sized based on the size of the conductors that are supplying this raceway. Okay? And over here, the same thing. This one right here, using, say, concentric, eccentric knockouts, then they're considered impaired knockouts. I have a bonding bushing with a bonding jumper based on the size of the conductors that are supplying this enclosure. Now, here's the main bonding jumpers, which are required in the service equipment. These are both service equipments. They are grouped together in one location. If this was factory installed, no sizing. If this is a wire, I would have to size it based on the size of the conductors that are supplying this service equipment. Okay, pretty simple concept here, right? All right, so the code allows me to use the grounded conductor to make all of these connections to this enclosures. And indirectly, it's also allowing me to do it as well with the main bonding jumper here inside of this service equipment. All right? Oh, let me go and tell you this. What if I had perfectly punched holes? If I did, then I could put a bonding lock nut on there with a screw that drives into the threading of the nipple, and I could put it here and here and here. If these were perfectly punched out holes, then I would be perfectly fine. I wouldn't need these bonding jumpers, supply side bonding jumpers. That would be considered adequate connection. Okay? But I can't use a standard lock nut except for the mechanical portion. So I could have it on this side, but on the side that's inside the raceway, or the gutter here, then I would use a bonding lock nut, or in this case, a bonding bushing with a bonding jumper, because I encountered some concentric or eccentric knockouts. All right, the method of bonding at the service. Various methods of bonding at the service are addressed by the code. We've talked about quite a few of them here. The bonding requirements are restrictive at service, are more restrictive as services than they are downstream. That is so very true. So you have to do all these things and have to make sure everything stays an assured type of bonding situation on the line side of the service equipment, or the service disconnection means. But on the load side, you can use standard lock nuts. Okay. Now, if you encounter an application where you have concentric or eccentric knockouts on a 277 application 480, then you just have to make sure that those concentric eccentrics are evaluated as part of that piece of equipment or that device box or whatever it is to handle that application, and then you could use a standard lock nut. Okay, if not, then you might need a bonding bushing or the bonding jumper for that application. So you need to look at that when you're dealing with those type of voltages. But what we deal with, and in most of those boxes that are heavy duty, already those concentric or eccentric knockouts have been evaluated for that higher voltages. But for normal 120, 240, 208, things like that, it's not really an issue. The normal concentric, eccentric on the load side, you can use a standard lock nut driven down tight. It bites into the metal of the enclosure. You're good to go. Okay, so that's kind of the difference where you can't do that on the line side, but you can do that on the load side. And we'll probably have a video or a webinar coming up soon, which I show you all the aspects of sizing equipment, grounding conductors, and bonding on the load side. And we'll get into more detail because I kind of just glossed over it. But we'll get into all the nuances in that maybe in a subsequent video. All right, let's get back to the PowerPoint. All right, so the service equipment and enclosures can be subject to heavy fault current, obviously, because there's no overcurrent protection device that we're aware of. Okay, it might be on the primary side of the transformer, but there is a potential for a higher level of fault current, and so we need to make sure those connections stay solid and done properly. And again, the overcurrent protection is controlled by the service utility. And I am going to just remind you again that all of those connections on to the service interconductors that come on the line side that's coming from the utility, they only have overload protection based on whatever the overcurrent protective device in the breaker that it's feeding in the panel. It's going to limit you. If it's a 200 amp panel, it's going to limit the load to 200. If it's a 400 amp main breaker, it's going to limit it to 400. So it's going to limit the load. But again, it does not limit the short circuit or ground fault. That's why we have to tie everything together to give the potential fuse on the line side a fighting chance to operate. And that is a tough one because it is on the primary side and we can't control what they do. We have a lot of rules on how we do that in 450 for transformers in the NEC, but we don't have anything to do with that on the line side. So we just want to make sure it has a fighting chance to do that. All right, so now let's look at the different methods. So let's see here. B is going to say, okay, of those allowed things that you got to bond together in 250.92a, here's the methods. So bonding jumpers, meeting the requirements. Oh, can I get my mouse working here? Okay, here we go. The bonding jumpers meeting the requirements of this article shall be used around impaired connections. We talked about that, such as reducing washers or oversized concentric or eccentric knockouts. Standard lock nuts or bushings, just a standard bushing, shall not be the only means of bonding required by this section. Okay, we're doing a little bit more enhanced type of bonding here, but shall be permitted to be installed to make the mechanical connection. Again, if it's rigid, you want to hold the raceway in place, you got to connect it to the box. Yes, lock nut to be there. But opposite the lock nut, we want to have some other method to do that. We can't rely on a standard lock nut. That's only for mechanical purposes. Now, electrical continuity at service equipment, service raceways, and service conductor enclosures shall be ensured by one or more of the following. Here we have bonding equipment to the grounded service conductor in a manner provided in 250.8, means threaded entries, all those type of things that are listed in that list in 250.8 is considered acceptable. Connections utilizing threaded couplings or threaded hubs, and we see that in all of my graphics where it comes into the top. You see the threaded hub. But what if I had, let's go back to me and I'll illustrate. On that overhead, what if I have 20 feet I had to go? So we got the hub on top of the meter enclosure, but now I need to go 20 feet up to the weatherhead. Well, every joint of rigid, let's say, is only 10 feet long, so I need 2 sticks. So they're threaded, and I'll have a coupling. That threaded coupling is bonding those 2 raceways together. It is acceptable to utilize that in order to get you that additional length of raceway you need. So that's the example, and it comes into that threaded hub. That's what we see in most of the graphics that I'm showing at this point. All right. Then it goes on to item 3. It says threadless couplings and connectors if made up tight for metal raceways and metal clad cables. Okay, so then also I can have threadless couplings and connectors once I make them up tight, even set screw tight. I can make up and it's acceptable. And then 4 says other listed devices such as bonding type lock nuts, which we're going to see pictures of in a minute, bonding bushings, or bushings with bonding jumpers. Okay, there are bonding bushings that also screw on that serve a role as a bonding bushing, but it also drives into the ring and makes the connection as well. So there's different selections to choose from. Now the methods, let's look at it here. The service conductors only have short circuit protection. Again, they only have the short circuit protection to that line side utility transformer. They have overload protection, as we talked about, due to that that service main overcurrent device, but that's only overload protection. Now, one reason the code limits the length of service conductors inside of a building, but requiring the service disconnect means to be nearest the point of entry of the service conductors. Again, how we describe that in 230.70A1. Again, it doesn't matter which jurisdiction you're in. Some jurisdictions let you go 3 feet. Some let those service conductors come into a building 10 feet, some 20 feet. I don't like that because that means that you have conductors inside of a raceway that are theoretically unprotected. There's nothing that we as an electrician have installed to reliably say that if they get energized, we're going to remove the current. We're certainly not going to rely on that transformer fuse. We are not. It is on the primary side. We don't know what they've done up there. We don't even know if they've done it right. We are tying everything together to give it a fighting chance. We're putting everything at the same potential. However, we do run the risk. So why would you want those service entrance conductors running inside of the building where somebody could come in contact with them? So the code says you can do it outside. You can run it any length outside or inside the nearest point of entry. Well, to me, the nearest point of entry is directly the point where it runs inside the building, the moment it penetrates the shell of the building. However, we understand that that isn't always practical, and sometimes you might have a working clearance issue in 110.26 that allows you to shift something to the left or right a little bit, but this was the only location that you could penetrate through the building. Then many jurisdictions will give you some leeway and let you go up to 3 feet this way, 3 feet that way, and what have you. Some will let you 6 feet. That's up to your jurisdiction. We don't govern that. The code just says the nearest point of entry. So if you were a literal purist of the code, and a lot of us kind of say we are, but we are kind of flexible. But if we were a purist, then what we would say is that disconnection means, or that service enclosure needed to be exact opposite of the point where it penetrates the wall. Or it can be outside, and I don't care where you put it. But, hey, on that building, that is. So whatever your jurisdiction does, fine. I would say keep it as short as possible. Again, remember, we don't have the same level of protection on the line side as we do on the load side. All right, let's get back to the presentation. Various methods of bonding at the service are illustrated on the next few slides. So here are your bonding lock nuts. Again, if you don't have concentric or eccentric knockouts, or you don't have any oversized openings, then you can use one of these. Now, here's a standard lock nut, which might be on the other side of this, or it might be on the outside where actually the raceway comes to the enclosure. And this is for mechanical purposes, perfectly acceptable. But this is not going to be your means of bonding. This is your means of bonding, as long as you do not encounter any eccentric or concentric type of knockouts. Now, what about bonding wedges? Now, the use of bonding wedges around concentric, eccentric knockouts or oversized openings are encountered. You can use these, okay? But where you do encounter it, then you need a bonding jumper. And you can utilize these with the bonding jumper. All right. Now, where there's no concentric, eccentric knockouts, then you don't need a bonding jumper, and you can drive this into the raceway, into the nipple, and then you'll have a bonding bushing or a bushing on top of this, or another standard lock nut on top of this, driving this tight against the enclosure. Okay. Again, standard lock nuts are permitted for the mechanical connection only, opposite the bonding wedge, but standard lock nuts are not to be used for the primary bonding purpose in this application on the line side of service equipment. Now, those other ones, just wanted to give you some illustrations. Threaded couplings and connectors, kind of similar to this. Again, used in RMC, IMC, and again in EMT as well. Hubs, we see all these hubs on a lot of the graphics I use coming in. It's threaded entry. These screws screw down into the equipment, makes a good solid connection through the threaded entry. And then, of course, here's the threaded coupling we were talking about, let's say for a rigid conduit raceway or IMC. All of that does give you adequate means to maintain the connection between all those components that have service entrance conductors within them. Here's an example of the hub, and here is an example of a standard lock nut being used for mechanical purposes connected for this equipment. I have no idea what's done in here, but this enclosure is connected here, so this nipple is connected to here, which means that this one is bonded per this application here. Here's just a close-up of that application. This is an example of a bonding bushing with the lug on it, and they're running the connection through it. Okay, here's what they look like. It lays in and it makes connection, and this right here will drive into the screws. All right, methods of bonding at the service, 250.92b. Again, we kind of went over all these, but you can use listed lugs, pressure connections, other listed means that are in 250.8, which gives you a laundry list of methods. And you can use any of these methods, not just one method in 250.8. You can use all of them. Threaded couplings, connectors, as we've talked about it. Threadless couplings and connectors, as we talked about it. Other devices such as bonding type lock nuts, bushings, and bushings with bonding jumpers. Again, reminder, standard lock nuts are not permitted for bonding on the supply side or line side application. Bonding jumpers are required to be used around impaired concentric or eccentric knockouts. Eventually, I'll know that I'm pronouncing that right. And connections cannot depend on solder. You cannot do all this in lieu of all this by soldering pieces together. Not acceptable. Now, let's talk about grounding at remote meters. All metallic equipment containing service conductors are required to be bonded together and to the grounded service conductor as stated in 250.92a. So, we're going to keep it really simple. When you're dealing with the remote equipment, like a CT cabinet or a meter enclosure that is remote of, let's say, the structure, or it's downstream, maybe on the same structure, but it's further down the wall or it's remote from it, keep something in mind. It still has service conductors in it. So don't get lost in all the names, like if it was a meter disconnect or anything like that involved or interposed in the system. This is a remote meter location. It's still got service conductors in it. That same level of bonding that required in 250.92a is still here. Don't get into a false sense that it's not associated with anything like the equipment, service equipment. It is still got service conductors in it. So keep that in mind. That's the thing that you always want to remember. Keep in that loop of safety when it comes to grounding and bonding. Now, this includes remote from the service equipment, meter cabinets, meter socket enclosures, current transformer cabinets, raceways, and auxiliary gutters. All of those things fall into this. Now, the grounding and bonding of equipment on to the grounded service conductor at locations on the line side of the remote and remote from the service disconnection means increased safety. It's no different. We were talking about that earlier when it came to the line side and all those raceways tying together increases the safety. The same rule applies here. Now, remote equipment should never be grounded only to a grounding electrode, such as a ground rod. Okay? It needs to be connected to the grounded conductor. Okay? I could drive a ground rod there, and I have to have my grounding electrode system at the structure itself. But I can't get away with having it only at the remote system. That becomes a hazard because any fault current in the service equipment could go down through the grounding electrode conductor, or actually, if you didn't have one in the service, any of the equipment could actually get energized over onto the earth through any type of incidental contact, and it could try to come back through the earth, up through that grounding electrode conductor into the remote meter, and it means that current's going to travel on a high impedance path. You're not going to trip the fuse possibly on the supply side or the primary side of the transformer. That becomes a hazard. Okay, now I'm permitted to have some kind of grounding electrode in the remote meter if I want to, but I can't do it in lieu of the connection at the actual service equipment. Now, the reason I say it's permitted is, let's bring it back to me, is because, be honest with you, it is done all the time at the utility when they drive them at the pole. Okay, it's connected to the grounded conductor. So the secondary side of the transformer has that connection that's connected between the actual winding, a midpoint of a winding to ground, and a grounded AC system is connected to the earth. So all you're doing at the remote equipment is doing the same thing as you would do at the service equipment. However, if you only did it at the remote location and not at your service equipment, well, first of all, you'd be violating the applications here. You need to maintain that location there. But by doing it only there, then you create that hazard. Can I do it at both locations? Sure. Now, if I do that, remember, the rules for the electrodes and the size of the grounding electrode conductor and all that are the same. It's not considered an auxiliary type of electrode. It is being done. So the case is, when I install grounding electrodes at a building, if I choose to use certain ones or put them all in, just because I had one, let's say a concrete encased electrode, and I choose to use another one, doesn't mean I have to make follow any rules any different. I still have to follow the rules. If it was a ground rod, for example, and it's being used, I'm adding it to a concrete encased electrode system, which I'm not required to do. All you need is the one. But if I was doing it, I have to meet all the requirements of 250.66A and B and C, depending on what type of electrode I'm using. Now, that application in that remote meter or CT, same thing applies if you choose to put a grounding electrode there and do it that way. All the rules have to apply, and I don't see anything in the code that says otherwise. Some may argue differently, but I don't see it, and it's just a safety concern. It's not for static like you would for an auxiliary. It is a requirement here to meet the requirements for that electrode and that grounding electrode conductor sizing and what have you. That's all I'm saying with that, okay? So don't get lost in that. I would prefer you not put one at the remote meter location. Not necessary. You're connecting to the grounding conductor within that remote meter, and we're going to see that here in a second in some examples. But I'm saying if you do put one, don't forget that you're required to do the one at the service equipment application, okay? That's the key. All right. Let's move on to the next portion. Again, remember, if you did it only at that one location, then there is no overcurrent protection on the will open or operate, leaving the equipment enclosure at a dangerous voltage to ground potential. And any person or animal that contacts the enclosure can be shocked or electrocuted. Okay? We don't want that to happen. So here's the example. This CT cabinet is 100 feet away. I did this by the depiction here. All right, so this enclosure is connected here to the grounded conductor, which we've already saw. That's perfectly acceptable in 250.142. This is a factory installed jumper here, supply side bonding jumper. So it is done and it already takes the place. If it was a wire, then we're going to size it based on the size of these conductors, and we've already gone over that. Here would be this one and this one added together. That's the size it's going to be. And you go to 250.102C1 and you're going to do that. Now, here's the permitted grounding electrode system, okay? Here's the required one over here, okay? And it's connected to the grounded conductor, which is connected here to the enclosure, brings everything together here, all right? Again, it's permitted to do it over here. Here's the one where we generally like to see in the application. Over here is permitted. The problem we say why this one's permitted is because we would prefer it to be done here at the service equipment over here than over here, because this is not service equipment. None of this is service equipment, okay? All right. And it just increases a hazard by doing it over here and not doing it over here. We really prefer to have it here in this application. All right. Now, this raceway right here, obviously, since I'm only running one, I have 3 sets here. So I take set A. This would be 500, 500. So it'd be 1,000 kc mil. That's the size of the conductors that are in this raceway feeding it. I size this one here based on 250.102C1 to determine what size that bonding jumper needs to be. So in this case, since we said it was 1,000 kc mil, we're going to go back to the NEC and we say, okay, it's 1,000 kc mil, so it's over 600 through 1,100. So that would be a 2-aught right here. A 2-aught supply side bonding jumper. All right, let's go back to the PowerPoint. All right, so that's how we do it. Now, here you notice that I used a bonding lock nut. Now, I painted these green to kind of illustrate what we're doing here. They probably aren't going to be green. It wouldn't be wrong if they were, but it's probably not going to require it to be green. Main bonding jumpers and panels, it's required to be of green finish. But here we're talking about something that's being utilized for a supply side bonding application. Now, here's it's done. You got regular standard lock nuts for the mechanical portion. Here I have a bushing with insulator in it because these are 4 and larger. So for abrasion, I've got that done. So this is the bonding that's taking place here. Now I don't have to have any jumper over here because these bonding lock nuts meet that requirement and it's all good to go. This raceway in the middle here that's connecting the two, again, that is already bonded here on the side where the service equipment is, and we just sized that a second ago. I don't have to do both sides. I only have to do one. Now, somebody asked me, what if these holes are punched? If they're punched, then I can get away with a bonding lock nut, just like I did over here in the remote CT cab. Now here's a bonding of a remote meter as well. This is probably what you're typically going to see in a residential application. So I've got the raceway coming down from the weatherhead. This is the service point up here on the left. I don't show anything of terminations to the utility. I just show the conductors coming out. Comes down the raceway, goes into the hub at the top. Acceptable. We saw this in 250.92b. And here's it bonds it to this enclosure, which bonds this hub, bonds it to this raceway, which this hub bonds it to the enclosure, which bonds it through this screw to the grounded conductor. And here we have the raceway going down to the structure. It doesn't have a bonding jumper on this because this was a perfectly cut hole. It wasn't no concentric or eccentric knockouts. There wasn't any impaired openings. So I used a bonding lock nut to make this application. Now, so all metal raceways and non-current metal parts of the equipment shall be bonded together to the system grounded neutral conductor within the enclosure. We've done that here. All bonding is in accordance with section 250.92b1 for bonding at the service. So we've bonded everything together. So we've done that. Lastly, the grounded conductor is being used per the allowance in 250.141 to bond the meter enclosure, as you see right here. Okay. Now, anybody out there would say, well, wait a minute, he's adding this grounding electrode system here, and you have a violation here. Well, like I said, if they used a ground rod, I would expect them to follow all the rules that are required for this. Now, they only have one ground rod, so silly me. They came and did a test on this graphic, and they determined that it was 25 ohms or less, so it only needed one ground rod. And also, it's above the ground, so there is going to be a protective cone placed over this. Also, this ground rod actually is 10 feet long, so there is 8 feet in contact with the earth. I only had the little bit sticking out for illustration purposes only. Do you believe all that? Okay. Anyway, that's our presentation today. Hopefully you got something out of it. I really appreciated presenting it to you. Hopefully you like this presentation and you want to see more. So visit our websites, Google online to Master the NEC, and you'll find that we have plenty of videos. Visit our website at masterthenec.com. Go to electricalcodeacademy.com. Go to our websites. Go to Facebook page. Google the Master the NEC on Facebook. You'll find our page. Go to our Twitter accounts, which is also at Master the NEC. And watch our videos. Watch some of our graphics I have posted up there. If you have any questions, you can always email us at info@masterthenec.com. Or you can send me one directly at info@electricalcodeacademy.com. And I'll answer any questions you might have. But again, thanks for hanging in there. This was about an hour and 30 minutes of a video. And so hopefully you learned something here. Again, remember, there's a more enhanced requirement for bonding on the line side of service equipment. Make sure you get it right. Let's give that fuse at the utility side a fighting chance and hope that it does something. But really, we're tying all those metal parts together, creating the same potential in the system, not trying to isolate any metal part which could create a hazard, following all these applications safely, and hopefully keeping a safe installation and keeping all of our customers safe out there. Thanks again for watching. God bless, and until next time, stay safe.